Section 5.1. Let's recall volume by slicing. We're looking at a triangular prism. Give some measurements: height h, length l, and width w. Pretty basic formula that the volume is 1/2 the length times the width times the height. The idea of slicing. Let's suppose that we have this triangular prism sitting in the first octant so that the base is in the xy plane, this purple shaded is in the xz plane, and the face opposite behind is in the yz plane. Take slices perpendicular to the xy plane and the yz plane, and then as you do, depending on the y that you pick, the height is going to change. Okay, so we have this face that is sitting in the first octant. Let's come up with an equation for that face. And it's pretty easy because we'll only need a relation between z and y. It is a cylinder, meaning that you can just pull it straight out and there's no change as you change x's. So doing so, you just have to come up with an equation of a line. Remember that up and down is z. Out from the origin to the right, y's get bigger. You have a z-intercept of h. Let y be 0, then z is equal to h. How big can y get? Let y get as big as L, and then you want it to cross the y-axis. So when y is equal to L, you get h minus h. Okay. Now, looking at this slice here, we have a shaded purple area. And as we move the slice, the area is going to change. Well, the base is going to be constant W. But as we change the position y0, our height is going to change. So coming up with the area of the shaded purple region is going to be the base, which is W, and then times z0. And then z0 is given by this, which is a dependence on y0. So for all slices, we have our area function, constant W, times the height. We know by the slicing method that we can recover the volume if we add up all of those areas, and this is a continuous addition, in other words, integration, and you want to do that for y's going from 0 out to L, from 0 out to L. Plug in the formula for the area, W times Z. Z is a function of Y. W is a constant, bring W to the front. Then you have the integral of the form of Z. This is a simple integrand, constant, and then linear in Y. Perform the integration, plug in the bounds, you only have to plug in the top, and then you recover back the volume. Very good, so that's slicing. And this was taking slices where we're perpendicular to the y-axis. I'd like you to think about how to redo everything, but with slices perpendicular to the x-axis. And I've given you a visual where you want to think about the area of this shaded region. And that's going to depend on x, where x is going to want to run from 0 out to W. And the nice thing here is that all of those slices, the a of x is going to be a nice constant. But go ahead and write all of that out and then verify that you do get the same quantity. So this is just using second semester calculus. Why am I going over it in third semester calculus? Well, if we look at these nice pictures, that the area that we were computing was by simple formulas, but we know that if we have some type of curve, to find the area underneath that curve typically will require calculus. And then for finding the area under that one curve, well, we want to do it for all curves that exist between 0 out to some value or 0 out to some value. which is the basic general notion behind a double integral. Very good.